Good morning, scientists. This is Dr. B, and we're going to walk through the first part, Activity 1, Constructing an Argument for Climate. The title of this unit is What is the Future of Earth's Climate? And HAZBOT, this thing out here, is one of the it's an automatic software AI program that kind of grades some of your answers. And those answers are not in this first activity, but it will give you a heads up when HAZBOT's going to grade your answers. We're going to talk about scientific argumentation. Now, there's, the regular everyday arguments like what's better, Snickers or Reese's Peanut Butter Cups? And you can have an argument about that. I like this one better. I like this one better. But it's not a scientific argument. Or you can have an argument with your parents where you disagree about something, but you're probably not using evidence. And using evidence to support your claim is the foundation of a scientific argument. That's the main difference between just having a regular old argument. You came home too late. You're irresponsible. No, I didn't. That kind of argument you might have with your parents. And the way scientists try out their ideas with each other by making a claim and supporting it with evidence. So let's watch this short video about how these two kinds of argumentation are different.
Scientific argumentation. What is it? It's true. No, it isn't. Yes, it is. Amy told me, so it's true. No, that's just an argument. Scientific arguments have lots of important parts. Claim, a statement. Explanation of a claim. Evidence and reasoning. Level of certainty. Explanation of certainty level. Limitations of the evidence or reasoning. Okay, we can see you are uncertain about this entire process. That's okay, you'll get it by the end. Scientists start with making a claim. Claim. Brown-eyed parents can have blue-eyed children. Here's another claim. Earthquakes are more likely to appear along fault lines. These are all scientific claims that can be backed by evidence collected by observation or experimentation. I have a claim. Chocolate ice cream is much better than vanilla. No way! Vanilla is the best! I like strawberry. Seriously? Actually, I don't like ice cream at all. Are these scientific claims? Can they be backed by evidence? No, these are opinions. Okay, let's think about evidence first. What is evidence? Evidence is data. Data comes from observations you can make in the real world. Or in a model. That's where reasoning comes in.
Let's stop for a moment and talk about evidence. If we wanted to support our claim about which candy bar was better, we might want to go to the data on the nutrition label here. So we can see that Snickers has 250 calories, so that could enter into our argument that this candy bar has more calories. Or we could talk about the amount of protein. There's 4 grams of protein in this candy bar. Or we could go to the Reese's Peanut Butter Cup nutrition label and look for evidence. We could talk about the number of calories. We could talk about the amount of protein or fat. So that would be evidence if we wanted to have a scientific argumentation about which candy bar was better. Our evidence could come from the nutrition label.
Reasoning the claim. Let's use a real example. Let's say you're planning to take a trip to New York City next week. You are looking forward to walking around the city and seeing the sights. Oh no, it looks like there is a hurricane forming off the coast of Florida. Yep, looks like Uncle Joe is going to get soaked. Will your trip to New York be rained out too? Let's examine the evidence. What data do we have? Here's the storm forecast. What is this map telling us? First, this map is a model that shows the projected movement of the storm. Is the hurricane going to hit New York? If so, when? Looks like it will hit Friday. It could hit Virginia instead. Yes, the model shows a range of times and places when and where the hurricane may hit. Good thinking. We cannot be 100% sure where it will hit or when. The storm is moving north, but its exact path is uncertain, especially the farther into the future you try to predict. Notice that the cone gets wider. This is the cone of uncertainty. 1 day forecast is very certain. 3 day forecast is somewhat certain. The 5 day forecast is even harder to be certain about. Scientists are most confident in their predictions when they have a lot of data. This computer model is based on lots of data like temperature, wind, barometric pressure, observations, and historical data from past hurricanes.
The same reasoning can be applied to climate change. So we can predict probably next year with much more certainty than we can the year 2100. There's more uncertainty because there are more variables that can change in the next 78 years.
Back to our map. We see that the storm will move up the coast and may arrive in New York City on Thursday or Friday. What scientific sources affect your certainty? Yes, there is a possibility that the storm will slow down and hit on Saturday. The speed of the storm could change. Indeed. The hurricane may change its path and bounce off into the ocean. Righto, we will be more certain when we get closer to the weekend. So, what did we learn? Scientific arguments start with a claim. Claim a hurricane will hit New York City before Saturday. Then there is an explanation of the claim, which includes evidence and reasoning. Explanation. The model shows that New York City is within the forecast path of the storm. If the storm continues on the forecast path, then it could hit New York City by Saturday. The level of certainty is 80%. Finally, there is an explanation of certainty. Looking at the map, based on the cone, the storm should hit New York City earlier than my trip, but the storm could slow down or change its path. We hope you enjoyed the show.
Okay, now that we've seen the video, we can go over the questions at the end of the video. What's the difference between a scientific argument and a regular argument? So we know a regular argument would be kind of like which candy bar is better, and you could say, I like Snickers, I like Reese's, and go back and forth. But if you wanted to make a scientific argument, you need to look for data. You could use the nutrition labels. You could say, well, Snickers has more calories or more protein, Reese's has more fat. You'd have to look at the nutrition labels and provide some evidence to make it a scientific argument. Largely, if you looked at the nutrition labels, you'd probably find out you shouldn't eat either of them and go have an orange as a snack. So the big difference between a regular argument, one you might have with your parents or your friends, and a scientific argument is scientists kind of try out their ideas, they make a claim, and then they have some evidence. So I'll give you an outline here. So scientific argument is make a claim and use evidence. And sort of an everyday argument is no evidence. You make lots of claims, but it's mostly just based on your opinion. Uncertainty is because models are not perfect. We don't have all the data. We don't know everything about how nature works. Is talking about uncertainty important? Yes, so we understand how much we should trust a particular idea. Things that make us uncertain or affect our level of certainty is our models. How good are they? How many variables they are? Simple models are good for understanding phenomenon, but they're not always best for making predictions. The more data we have, the better predictions we can make. For example, when I'm looking for weather information, I like to go to Wonderground because it doesn't use just the National Weather Service stations to make predictions. It uses everyone's backyard weather stations all over the United States and all over the world. So it has more data, so it makes better predictions. How far in the future are we trying to predict? The more, just like the hurricane, if we're trying to predict way into the future, we're going to be more uncertain. If we're trying to predict the climate next year, we're going to be more accurate than trying to predict the climate in 2100. And new information is always appearing about how Earth systems work and how Earth systems affect the climate that we don't know yet. And so we're always refining our models and making them better. So in this climate activity, you'll be asked to answer a series of questions that ask you to choose a claim, support that claim with evidence, and explain how certain you are about your answer. The red text helps explain what you should include in each type of answer, and the gray text shows an example answer that you can use as a reference. We're going to give it a try. We're going to be talking about this graph here that shows the Earth's air temperature and solar activity from 1880 to 2009. Solar activity includes sunspots, solar flares, and other solar weather events. The light color lines, like this pink line here, show yearly measurements, and the darker lines show running averages. So if we took, let's say, 1911, for the year 1911, that line right there at 1911 would be an average of 1911, 1910, 1909, 1909, 1908, 1907, 1906, 1905, 1904, 1903, 1901, and 1900. So 11 years would be average to make this 1 point. And then in 1912, they'd use the previous 11 years. So 1912 to 1901 would be average to make that point. So that running average smooths out the data. They did the same thing here with solar irradiance. An important thing, when they put two lines on one graph, you can see they usually color code it. So this line here, the blue line, has the blue y-axis here. And these numbers represent solar irradiance. If you have a red line, you look over on the red axis here to find the values for this line. What quantity is shown on the x-axis of the graph? Well, let's use the label, year. Which color line shows the temperature over time? Well, let's read the title of the graph. Temperature is in red, solar activity is in blue. There are 4 sets of lines on the graph, 2 for temperature change and 2 for total solar irradiance. 2 of the lines show the yearly readings, and the other 2 show the 11-year average for those readings. What's the average temperature change reading in degrees C for the year 2000? So average would be about right here. So it's pretty close to 0.05. Remember, for the red line, we want to use the red axis, red y-axis. So now here are some hints on how to make a claim. A good claim is based on evidence. Evidence may come from graphs and charts. Evidence may also come from models that you run. And we'll be doing that later in the unit. Based on the graph, is Earth's temperature dependent on the level of solar activity? Well, here maybe, because these lines kind of match. But from 1960 to 2000, I would say no, because solar irradiance is going down and temperature is going up. So I said no. And I wrote my explanation and said solar irradiance is going down from 1960 to 2000, which are the years where humans have been affecting the climate the most. The temperature is going up. The graphs don't match in the years 1960 to 2000, which is the period in which humans added the most greenhouse gases to the atmosphere. So probably people had the most effect on the atmosphere, more than solar irradiance, in those last years, and we'll probably continue to see the temperature go up no matter what happens with solar irradiance, unless we do something drastic to fix our climate. The level of certainty here, I picked a 3 kind of in the middle, because there are a lot of things we don't know. I want a little bit more, I want a mathematical model here. I would like to know the level of mathematical correlation here, and correlation is just how much of a prediction. Like if you give me solar irradiance, if there's a strong correlation or relationship between the two sets of numbers, I can make a prediction about what the temperature is going to be. I could do that in the first part of the graph, but I can't really do that in the second part of the graph. So I would kind of like to split the graph in half and look at the mathematical correlation between temperature and solar activity. And I would also like a lot more data to see if they always follow each other like this. It would be great if I had data back to like 1380, another 500 years of data, so I could look at the different relationships, the different fluctuations of solar irradiation and Earth's temperature. But I don't have that data, so my uncertainty is a little bit more than I would like it to be. Here's an example of a certainty explanation. I'm pretty sure about my answer because the graph shows solar activity does not correlate with temperature over the entire time period. The temperature continues to rise while the solar activity decreases. Solar activity may play a role in Earth's temperature, but it's not the only one. If it were the only factor, or even the main factor, solar activity should be clearly correlated with temperature change across all time periods. So this person is saying, I want to see a correlation all the way across the graph. And that's what I would like to see as well. I don't see that, so I'm kind of uncertain. I don't think they have much to do with each other, especially now when greenhouse gases are probably affecting the temperature far more than solar irradiance. The graph does support that explanation. So here's Hasbot. Hasbot is going to give you feedback on your answers as you go through this module. Hasbot is an AI program that reads your answer and gives you feedback and gives you a score. So if you do a good explanation, you're going to go 4 or 5. If your explanation isn't so great, you'll probably get a 2 or 3 and some hints on how to make your explanation better. Read those hints, try again, and resubmit. So in the module where there's an argumentation item, you'll see a question mark here, and you can get some hints. For example, here it says the real correct answer is B. Checking on the question mark will give you some hints about how to choose a claim. Write an explanation, select a certainty rating, and write a certainty rationale. Feel free to check your answers for completeness before submitting them to be scored. Click on the hint for this question to select the real correct answer. So we know B is the real correct answer because we found it in the hint up here, and we can hit check answer. Yep, we got it correct. Awesome. So we'll be doing that throughout the module, checking our answer and maybe getting some hints. So now that we're done with the first part of the module, that wasn't so bad, huh? We're going to check show all answers. We can see our answers printed here. And in order to print them out, we want to find at the top of your iPad, it's a little square with an up arrow. You press that square with the up arrow, you get a little menu that comes up. There'll be tiny blue options word at the top. Click Options, click PDF, click back out of the menu, and then click Notability and send your answers to Notability, and you can hand them in through there. Thanks so much for watching. I'll see you during activity 2.